Recurrent neural networks are a fundamental architecture in the processing of data sequences, such as text, audio, or time series. Unlike traditional neural networks, these receive an input at each time step and generate the corresponding output, maintaining internal connections among their cells, allowing information to flow along the sequence. However, this type of architecture can have problems when processing very long sequences, mainly due to the issue known as gradient explosion and vanishing, causing important information to be lost during the learning process. To solve this problem, the long short-term memory architecture was developed, a variant of recurrent neural networks that incorporates gating mechanisms that regulate the flow of information. Looking inside one of these cells, we can see how the connections between cells allow information to flow from one moment to another, enabling the network to remember or discard information over time. Within each cell, there are several gates that decide what information is relevant and what is not, thus facilitating efficient data management as it is processed along the sequence. The key point is the state of the cells. The horizontal connection on top allows information to travel throughout the network with very few interactions. First, we have a layer called forget gate layer that decides what information to remove from the current state of the cell. The next step is to decide what new information we are going to add to the cell state. This is done in two parts. First, an input gate layer decides which values we are going to update. Then a vector is created with the information of the new values that can be added to the state. And now it's time to do it. In this step, the cell's previous state is updated based on the decisions made by the previous gates. First, the network forgets the irrelevant information, and then the new information is added. Finally, it is decided what we will send as the output of the cell. This decision is taken based on the state of the cell, the current input, and the previous hidden state. First, a layer called output gate uses the input and the previous hidden state to determine which parts of the current cell state will be relevant for the output. Then, we filter the cell state through an activation function and multiply it by the output gate, thus obtaining the output at the end of the cell. Now that we have the main idea about the functioning of an LSTM, let's see how they can be used in the real world. We will analyze Amazon's stock market. To train our model, we will use the historical closures of the company. In the chart, we can see an upward trend. Analyzing this type of data helps us understand how the shares have evolved in the past and establishes a basis for future predictions. The model we will use is configured in two layers, the first with a dimension of 128 and the second, 64, each one adapted to process and learn from the sequence of price data. We will train the network to minimize the mean squared error, a common metric for evaluating prediction models in time series. Once the model has finished training and we have made the prediction, we can see how the result obtained is quite close to reality. This allows us to see the effectiveness of the model and could also be used to make decisions about future investments.